Hello everyone, this is the lab number 6 interference. In this video we talk about the theory part of this lab. The objective of this lab is to study the interference by using Michelson interferometer. So this is the instrument, and we will learn interference by this instrument. So first of all, theory and equations used in this experiment. Okay, so here is a very big paragraph. Okay, we just go through briefly. Then we go to the figure about the interferometer. Then later that will be more clear. So Michelson interferometer is an equipment producing interference fringes and determining the wavelength of monochromatic wave. And wavelengths. Okay, this is the keyword shown in figure 6.1. The figure I'll show you later. So, in the Michelson interferometer, there are several things inside. First of all, we should have a laser. The laser is same with the last time we used in the lab 5. That's the helium neon laser. So the laser beam wavelengths with this size. Then after the laser beam, it's split into two beams by the beam splitter. Okay, one. This is the first part of the interferometer. First one is beam splitter. Then after the beam splitter, the beam separate into two beams. So beam number 1 hitting a fixed mirror. So fixed mirror, this is number 2, and reflecting back to the beam splitter, and finally we go to the viewing screen. Viewing screen is number 3. The second beam is beam number 2. Okay, second beam come here, hitting the movable mirror. This is number 4. And recombining with the first beam on the viewing screen. This viewing screen is number 3 we mentioned here. Okay, number 3. So this is the whole process until now. This is the whole process of the interferometer. It is that, okay, we come here directly. So first of all, it's a laser. This is a helium neon laser. Then we pass a lens. Then go to the beam splitter. So after the beam splitter, we have number 1, beam number 1, and beam number 2. It's one beam is from the beam splitter. The laser goes through, and another one is beam hit the beam splitter and reflect to the movable mirror. Then both of this one and this one, they are mirror. So after they hit the mirror here, after they hit the mirror, they will reflect back to the the laser will be reflected back. Then finally they will onto the viewing screen. So for this machine, then finally we will get a interference pattern at the viewing screen. That's the point. Then on the viewing screen, call it interference pattern. Then let us come back. So similar like what we said before in the diffraction lab 5, there's a bright fringe and um, dark fringe. So in here, we give them the name bright fringe. Bright fringe, it is constructive interference pattern. Dark fringe, it is destructive interference pattern. So here, constructive and destructive interference occurs depending on the phase relationship between these two beams. So they will have the phase relationship, and I will mention it after this part. If the movable mirror is moved forward or back, so the movable mirror here, movable mirror this one, we'll have a micro, and we'll have a micrometer here. We can change the position of the movable mirror. Since the movable mirror is moved forward and backward, the circular fringe appear and disappear. So we will have a circular fringe here at the viewing screen. It will be like a circle, circle bright fringe and circle dark fringe. So the appearing of the bright and or dark fringe equals delta m equals to 1. Delta m means the number of the bright or dark fringe, the number of that. D1 is the initial location of the movable mirror, and D2 is the new location of that mirror. And counting the number of the appearing of delta m fringes, so delta m is the number of the fringe at the center while moving the mirror with the distance d2 minus d1. Then the wavelength lambda of the light source can be determined. So lambda here, d2 minus d1 means the new location d2 with the minus the initial location d1 times 2 equals to delta m, the number of fringes, times lambda. Lambda is the wavelength of the laser. So that's the, until here, this is the first page of our handout. And after that, I'm going to teach you we call the phase relationship here, with phase relationship between those two beams. Here, first one, we'll have tell you what is the constructive wave interference. The first one is constructive interference, and second one is destructive interference. I've mentioned before, the light is a wave. The light behaves like a wave, and we use the sine or cosine wave to describe it. For example, it looks like this one. So number 1, then number 2. Now we call the phase relationship. So it means that the place we put the second wave. So for the constructive case, we assume that they are in the same position. All the phase, they are same. So it'd be like this. Then the peak of the wave, they're the same position, and the valley of the wave, they're the same position. So finally, when we meet with each other, they mix with each other, then we'll get what we call constructive interference, and which is the bright fringe. The bright fringe, then they will everything they will construct. So it will be the bigger the amplitude of the wave will be 2 times with before. This is the constructive interference. So come to destructive wave interference. So come to the destructive wavelengths. Say that. So okay, number 1, a wave here. Then number 2, they will have they move to, we call phase move a little bit, the back forward. Then the valley overlap with the peak. The value of number 1 overlap with the peak of number 2. Then the valley peak of number 1 overlap with the value of number 2. In this case, when they meet with each other, they mixed with each other, we'll get the dark spot, the dark fringe we call destructive interference. And after that, they will just like a straight line, right? Because the peak plus the valley, and the valley plus the peak. Also, like this kind of place, they are, one is negative, one is positive. But when they plus with each other, then they will like cancel. And finally, we will get a straight line. So that's why this is the bright fringe. It's the bright fringe. Then this means the dark fringe. Okay, just now we know the constructive interference and the destructive interference. And now we give an example for destructive interference. So for the upper one, it is number 1 wave, and lower one, which is the number 2 wave. Okay. The number 2 wave is from the movable mirror, and number 1 wave is from the fixed mirror. So, and we see here, it is the here is the peak with the mixing with overlapping with the valley, and the valley overlapping with the peak. So this is a destructive interference, and we got the dark fringe already. Then now we move the number 2 wave to the other place. We move the number 2 wave in this direction, and we go to see where is the next position we can get the dark fringe, and it should be here. Yeah, so it should be here. And then we don't care about the data, we read the shape. We don't care the data, so we just focus in this box. The new one, new number 2. This is number 2, new number 2, and with the number 1, we have the valley and peak overlap with each other. So they got it's here and here, and we got the destructive interference. Then we come to see that. So this is the position D2. This is the position D1. Now we just say we only move D2. Then all the D1 always fixed. we move the D2 to here, this is the new D2, then the distance of the D2 move is that 1 lambda, which is the size of here. Is 1 lambda. Then we go to find the next position. We can get the destructive wavelength is here. So we start from here. This is the number two beam line. Then the distance here is 2 lambda. We can see that D2 minus D1 equals to 0 times lambda. Then after that, for the second case, we want to get another dark fringe, and D2 minus D1 equals to 1 times lambda, and D2 minus D1 for the third case, which is 2 lambda. So later on, we will see that. So since we got the 0 dark fringe, then it is this distance. We just move it. Okay, that's a 0 dark fringe. We get 1 dark fringe already. Then now also get another first one dark fringe. Then it is 1 times lambda. Then we go to second dark fringe. Then we get 2 lambda here. So that's the first step. In our handout, we define that D1 is the initial location, D2 is the final location. So D1, so we have the formula 2 D2 minus D1, we get delta M times lambda. But here, what we get from here, it doesn't look like that. So where's the 2 comes from? 2 is that we use the movable mirror. So I'll draw a small picture here. When we have the laser, we got a lens, then we have a beam splitter. After that is the mirror, which is a fixed mirror, and other part is a movable mirror. And here we have a screen, viewing screen. And the laser comes to here, hit the beam splitter, come to the mirror, then reflect it back, go to the viewing screen directly, and the other, this is the okay, we see this is the laser number 2. And the laser number 1 is the laser go across the lens and go to the beam splitter and goes through the beam splitter, hit the mirror, bounce back, reflect it to the viewing screen. This is beam number 1. When we move the mirror forward and backward, then indeed it is double distance of the, because it has a reflection here. So we just say this one wrong. There's one way come in and one way come out. So when we say we move a D here, we want to move D here, but the laser goes through to D. But the distance laser path is 2D, so it should times 2. So that's why, because it has this kind of thing. That's why we will have this one. We have a 2 in front of our when we tuning um, uh, the distance. This we will tuning a micrometer here. We will tuning a micrometer here and make it the movable mirror forward, backward. Then after that we should times the 2. So that is the formula we give in our handout. Now we come back to the handout of the report. So in the report, the thing's not that much. We only have this one table. We'll count the number of the interference fringe delta M, and finally determine the wavelength of the helium neon laser. So one thing is you are going to count the delta M. In the experiment video, you'll count it. So first, when the D is, we will read from the micrometer. So before you go to count the delta M, then you read D1 on the micrometer, D1. Then write for example, start. When we started, it's 0. Then after that, when you count 1, 2, 3, 4, 5 to 10, then you write. For example, is 6.5, and this is the micrometer like this. And after that, you get dm. This is d1 minus d2. It's 60.6.5 like this. Then after that, you have the 20, 40, 60, 80, and 100 until 100. You can read it. You can count it on the. You don't need like for example, you stop at 6.5, then you pause the video. You go to read the number on the micrometer. After that, you can continue, or you can start from any point. Maybe you just said, okay, we start from this one. At that time you read the D1 from the micrometer is 8.7, 8.5, 8.7. Then you count 20 fringe. Then after that you will record another D2, D2 a number here, for example 13.5, like this. It's okay. So what I mean is that you can start from any place you want. And so that's a long video, that's have several minutes. Then you can start from any place. Then you'll get several dm here. Then you'll get and then after that you calculate from, you can get the lambda each time. So you can get a lambda 1 here, 2, 3, 4, 5, 6. That's it. Then finally, you need to calculate the error of the lambda, which means use your lambda minus the lambda in experiment, which is the lambda increment is the 632.8 nanometer. Then minus, use yours, minus the experiment and divided by yours, and after that times 100%. then you get the error of the lambda. After that, you need to plot. You need to draw a graph. You need to draw a graph between the delta m and the dm. Between the delta m and dm, because we have this equation d1 minus d2 2 times delta equals to delta m lambda. So when you plot the graph, the lambda will be the slope of the graph, and you can get the lambda from the slope. And in this one, we don't have the error, so it doesn't have the error bar. We don't have the uncertainty, so we don't have the error bar. So finally, the slope will be the graph will be looks like, draw here. This is 2 times d1 minus d2, but it's up to you. You can carry 2 or without 2, it doesn't matter. Then delta m here, or you get a lot of dot, several dot like this. For example, yeah, it'll be like this, and you plot a line. Finally, calculate what is the slope of this one. And the slope equals to lambda. The slope equals to lambda only you set the axis equals this axis defined is 2 times d1 minus d2. Okay, only in this case. So after that, you need to do a little bit calculation about how you get the calculation is about your graph. Then tell us the slope. Finally, you get. Then finally, it's the conclusion. Several sentence about this one. Then that's all the report for the lab 6.